Good evening, everyone. Good evening, good evening, good evening. Good evening, everyone. Am I audible and visible? Please type in a chat box. Am I audible and visible? Good evening, everyone. Good evening, good evening. Everything is fine. Okay. So, shall we start today's session? Shall we start? So, beta, whatever we discussed in the previous class, that is clear to everyone. Whatever we discussed in the previous class, that is clear to everyone. So in previous class, right, in previous class, we discussed about the syllabus, right? We discussed about the mechanical syllabus, chemical syllabus, civil syllabus, and also syllabus related with the XE part, right? XE paper. And also we discussed about the content of this particular course, right? And after that we discussed about weightage of the subject, right? What is the weightage in gate examination? What is the weightage of fluid mechanics in ESE examination, right? We already discussed this part, right? And also we discussed about the books, right? Which book is best for the practice purpose and which book is good for the learning purpose, right? We already discussed this part. Then we discuss about the subject, right? Then we discuss about the fluid mechanics. So first we learn about the mechanics. Actually, what is the mechanics? After learning mechanics, then we discuss about the fluid mechanics. So basically the fluid mechanics is the branch of science in which we are dealing with the fluid and its behavior. The fluid may be static, that fluid may be in motion, right? The fluid may be static and the fluid may be in motion. And what is the meaning of the static? What is the exact meaning of the static? That we already discussed in the previous class, right? That static doesn't mean stationary, right? A fluid, in case of the static, a fluid may be stationary or maybe moving with some constant velocity, right? So static doesn't mean stationary. Static, in case of the static, the fluid may be stationary or maybe fluid is moving with constant velocity. After that we discussed about fluid kinematics wala part, right? In fluid kinematics, basically fluid is in motion, but cause of the motion is not considered, right? If I'm talking about the fluid kinematics part, in fluid kinematics part, fluid is in motion but cause of the motion is not considered. Basically in fluid kinematics, we discuss about the velocity, we discuss about the acceleration, right? Whereas in case of the fluid dynamics part, in fluid dynamics part, fluid is in motion and also the cause of the motion is considered. Cause of the motion is considered, right? And after that we discuss about the rigid body motion, right? We discuss little bit about the rigid body and the rigid body motion. Then we discuss about the difference between the solid and the fluid, right? What is the difference between the solid and the fluid, right? So I hope that difference part is clear to everyone, right? If I'm talking about the solid can resist tensile load, solid can resist the compressive load, solid can resist the shear load by showing some definite amount of deformation, right? But if I'm talking about the fluid never resists the tensile load. Fluid never resists the tensile load. Fluid resists only 3-dimensional compressive load, right? one dimensional compressive load, two dimensional compressive load, fluid never resists. Fluid only resists three dimensional compressive load. Now if I'm talking about the shear, right, if I'm talking about the shear, so fluid resists the shear load, right, fluid resists the shear force by showing some rate of shear deformation, right? And in this way we are able to define the definition, in this way we are able to define the fluid. What is the exact definition of the fluid, right? In the definition of the fluid, why we are talking about the shear load? Are you getting my point? Why we are not taking why we are not talking about the compressive load or shear, why we are not talking about the compressive load or tensile load, why we are talking about the shear load? So I hope you can understand this, right? So after discussing the difference between the solid and fluid, we are at that stage to define the fluid, right? And what is the fluid? What is the fluid? We already defined the fluid. What is the fluid? So fluid is a substance which deform continuously under the action of shear force or shear load. How small that shear force or shear load doesn't matter, right? The value of shear force may be as small as possible, but you are getting some continuous deformation, and this continuous deformation is called flow, right? This continuous deformation is called flow. And in case of the liquid and in case of the gases, this continuous deformation occurs, and that's why liquid and gases are considered as the fluid. So beta, I hope till this point that is clear to everyone, right? Now come to the today's lecture. Now today we will discuss some fundamental fluid properties, right? Today we will discuss some fundamental fluid properties like what is the density, what is the weight density, what is the specific volume, what is the specific gravity. Then we will discuss about the viscosity, right? So in today's lecture we will discuss about some fundamental fluid properties, and in viscosity topic we will discuss about the Newton's law of viscosity, and also we will see the number of cases related to the Newton's law of viscosity. And after that we will solve some beautiful problems. Okay, but before starting the fundamental fluid properties, let's discuss about concept of continuum, right? Before starting the fundamental properties of the fluid, let's discuss about the concept of continuum. What is the concept of continuum? This is the you can say in fluid mechanics, this is one assumption, right? The concept of continuum is valid. Actually, if I'm talking about the fluid mechanics, so fluid mechanics is categorized as the statistical fluid mechanics and the classical fluid mechanics, right? If I'm talking about the fluid mechanics, so fluid mechanics is categorized as statistical fluid mechanics and the classical fluid mechanics, right? So whatever we discuss in our undergraduate syllabus or in our BTech syllabus, that is the classical fluid mechanics, right? Not statistical fluid mechanics. In our syllabus, right, in our BTech syllabus, in our competitive examination syllabus, right, the classical fluid mechanics is the part of our syllabus, right? So what is the basic difference between the statistical fluid mechanics and the classical fluid mechanics? So beta, in classical fluid mechanics we assume this concept of continuum is valid, right? Concept of continuum is valid. But what is the concept of continuum? So beta, in concept of continuum we assume that the fluid is continuous. We assume that fluid is continuous. We know if I'm talking about the fluid, that means, right, see, and please try to understand that when very important point, whenever I say beta fluid, right, whenever I say fluid, that means I'm talking about the liquid as well as gas, right? Whenever I say fluid, so I'm talking about the liquid and gas. But when I say liquid, so I'm talking about the liquid only. When I say gas, then I am talking about the gas only, right? But when I say fluid, that means I am talking about the both liquid as well as the gas. Now, if I am talking about the concept of continuum, so in concept of continuum, we assume that the fluid is continuous. That means the interatomic distance between the two molecules of the fluid we consider as a negligible, right? The gap between the two fluid particles we assume that is negligible. We can assume no gap between the two fluid particles, right? That means fluid is continuous. So in the concept of continuum, we assume this fluid is continuous, right? See, if I'm talking about the solid, in case of the solid, I can say the concept of continuum is not required in case of the solid, right? If I'm talking about the solid, we know that in solid, these are the solid molecules, right? These are the solid molecules, right? The solid molecules are very close to each other, right? So automatically in case of the solids, the gap between the two solid particles are very small. Are you getting my point? In case of the solid, the gap between two solid particles are very small, and that is the reason in case of the solid, there is concept of continuum is not required. But in case of the fluid, and if I am talking about this is solid. So if I am talking about the liquid, so let us consider these are the liquid molecules. These are the liquid molecules, right? These are the liquid molecules. And if I'm talking about the gases, so these are the gases molecules, right? These are the gases molecules, right? So these are the liquid particles, and here these are the gas particles, right? So in case of the solid, it is very much clear. The distance between two molecules is very small. Whereas if I'm talking about the liquid, see, the distance between two molecules or two particles is, right, there is some difference, there is some distance between the two particles in case of the liquids. And if I'm talking about the gases, in case of the gases, that interatomic distance is large as compared to the liquid. So that means here the fluid is not continuous. Now there is some gap. See, this is the molecule number 1 and this is the molecule number 2. In between molecule number 1 and molecule number 2, there is a gap, right? But in case of the concept, in the concept of continuum, we assume that this gap is negligible. Right? Now see, what happened if we are not considering the concept of continuum? If I am saying the concept of continuum is not valid, right? But if concept of continuum is not valid, then it is not possible to define any property as a continuous function of space, right? If we assume concept of continuum is not valid, then it is not possible to define any property, either it is a density or it is a thermal conductivity or it is a viscosity or it is any property. It is not possible to define the property as continuous function of space. And if you're not able to define the property as a continuous function of space, then the mathematics will not help you, right? Mathematics will help you if the properties are continuous function of space. So if you're not assuming concept of continuum, right? If concept of continuum is not valid, not valid, then it is impossible, to define, any property, like density, thermal conductivity, viscosity, etc., as function of space, and if you are not able to define the properties as a function of space, then maths can't help you. What? See, maths is a tool to understand the science, right? Maths is a tool to understand the engineering, to understand the science, and in this case maths cannot help you, right? So maths can't help you, right? If you are assuming, if you are considering the concept of continuum is not valid, then maths will not help you. Right, now try to understand this concept. Let us consider a container. This is a container, and in this container let us consider some fluid, right? So these are the fluid particles. Okay, now I want to define the density, right? So what is the density? Everyone knows what is the density. Rho is denoted, or density is denoted by a Greek letter which is rho. So rho is a density, and density is nothing but the mass per unit volume. Right, and for differential element we can write density as dm by dv. Fine. Now this is a container, and in this container these are the fluid particles. Right, now see, I want to define density at this particular point. I want to define the density at this particular point. I want to define the density. So beta, if I ask you what is the density at this particular point, see, what is the density here? Can anyone tell me what is the density here? Let us consider this is the small elemental volume, that is, dV. Right, now in this small elemental volume I want to define the density. So can anyone tell me what is the density? Can anyone tell me what is the density? The density is 0. Why it is 0? Because in this small elemental volume, there is no particle, there is no fluid particle is present in this small elemental volume, right? So if I want to define the density for this small elemental volume, that density is 0. Are you getting my point? Yes, exactly. There is no fluid in this volume. There is no fluid particle. So if I ask you what is the density for this small elemental volume, so that is density is 0, right? So to define the density of this fluid, you have to consider the elemental volume in such a way there should be number of particles, there must be number of particles are present. Now see, if I am enlarging this elemental volume, if I'm enlarging this elemental volume, let us consider this is the volume. Now my volume is this, right? Earlier my elemental volume is this much. Now I'm enlarging this elemental volume. Now this is the elemental volume. Now it is possible to define the density here. If you enlarge the control volume, or if you enlarge the system, let us consider this is the system. Now if I'm enlarging the system, then it is possible to define the density. Tell me. Yes, it is possible to define the density. Yes, definitely we are able to define the density if I'm enlarging the system size, or if I enlarging the control volume, if I or I can say if I'm enlarging the small elemental volume size, right? That means beta, concept of continuum valid or not, right? Or I can say the validity of concept of continuum, validity of concept of continuum, validity of concept of continuum depends on the size of the system, right? Size of the system. If this is the size, or this is the small elemental volume, so it is not possible to define the density. But your elemental volume is this much, then it is possible to define the density, right? That means at this point there is no density. See, at this point there is no density, but at this point there is a density. Are you getting my point? Right. So beta, concept of continuum, as per the concept of continuum, we assume that gap between the molecules are negligible. So see here, the validity of concept of continuum depends on size of the system, or I can say characteristic length of the system, and mean free path, right? So let us consider L is the characteristic length. Characteristic length means it shows the, or it represent the length of the, it represent the size of the system, right? If I'm talking about the L is the characteristic length. So L is basically L represent the size of the system. So L is the characteristic length. And what is the lambda, or what is the mean free path? The mean free path is denoted by lambda, mean free path. Lambda is the mean free path. And what is the mean free path actually? What is the mean free path? See, this L is clear that L represent the size of the system. But what about this lambda? What is the mean free path? Lambda is the mean free path, but what is the mean free path? So beta, this is the statistical average distance, traveled by molecules to collide, by a molecule to collide adjacent molecules, That is the mean free path. Right? And this ratio, the lambda by L, see, the lambda by L, this ratio, the characteristic length versus mean free path. Obviously, this lambda by L, this ratio is a dimensionless. Tell me guys, yes or no? This ratio is a dimensionless? Yes or no? So this is a dimensionless number. Tell me. This ratio, this lambda by L, this ratio, lambda and L, the ratio of lambda and lambda is a characteristic size or physical size of the system. And what is the lambda? Lambda is a mean free path. So this ratio is a dimensionless number. And this dimensionless number is called Non-continuum number. This dimensionless number is called Non-continuum number. This dimensionless number is called Non-continuum number. Right. So that Non-continuum number shows the validity of concept of continuum. Right. In exam, it is asked that which dimensionless number represent the, or which dimensionless number shows the validity of concept of continuum. So that dimensionless number is a Non-continuum number, or you can say Non-continuum number, and it is a ratio of lambda by L. So beta, if this Non-continuum number, if this Non-continuum number Kn is less than 0.01, right? If this Non-continuum number is less than 0.01, then concept of continuum is valid. Then concept of continuum is valid. Then concept of continuum is valid. Right. Non-continuum number is less than 0.01 means, देखो, see, lambda by L is less than 0.01, or we can say, right, this L is greater than 100 times of lambda. Right. See, we can say na, right, lambda by L is less than 0.01, or we can say if L is greater than 100 times of lambda, if L is greater than, if the physical size of the system, right, here in this case, the selection of the system in such a way, that L is greater than lambda time, L is greater than 100 times of lambda. In such case, the concept of continuum is valid. In this case, concept of continuum is valid. So you can select your size of the system in such a way that is greater than 100 times of lambda. Then concept of continuum is valid. Are you getting my point? Is it clear to everyone? And beta, if L is less than 100 lambda, if L is less than 100 times of lambda, then it is not possible to define the properties as a function of space. If L is greater than 100 times of lambda, then yes, we can define any property, as function of space, But if L is less than, or I can say, if this non-continuum number is greater than or equal to 0.01, then in this case, concept of continuum is not valid. Concept of continuum is not valid. In this case, concept of continuum is not valid. Right? That means in this case, the L is less than 100 times of lambda. Right? So in this case, it is not possible. It is not possible to define property as function of space, because discontinuity present between fluid particles discontinuity present between fluid particles or gap present between the fluid particle is come into picture. Come into picture. Is it fine? Right. Now, see here. Now, non-continuum fluid. In case of the non-continuum fluid, in case of non-continuum fluid, in case of non-continuum fluid, non-continuum fluid means cases where concept of continuum is not valid, right? Can anyone tell me the cases where concept of continuum is not valid? Can anyone tell me? Can anyone tell me the example, or can anyone tell me the cases where concept of continuum is not valid? So see, in case of node point, gases which are present at the higher altitude, right? Gases which are present at higher altitude, concept of continuum is not valid, right? Concept of continuum is not valid. Concept of continuum is not valid. Concept of continuum is not valid. Case number 1, for rarefied gases. For rarefied gases, concept of continuum is not valid for rarefied gases, right? Rarefied gases means gases which are present at higher altitude, right? Gases which are present at the higher altitude, that is called the rarefied gases, right? Rarefied gases, right? So we know that at the higher altitude, pressure is low. At higher altitude, pressure is low. And if pressure is low, that means in a given volume, the number of fluid particles, or I can say the number of air particles are less, right? If pressure is less means in a given volume, the number of molecules of the gases are less, right? That means pressure decreases, right? At higher altitude, pressure is low, therefore density is also low. That means at a given volume, if I consider a given volume, in a given volume, the number of molecules are very low. So let us consider these are the number of molecules. And if number of molecules are less, that means that if the number of molecules is less, that means the lambda is more. That lambda is nothing but the statistical average distance traveled by the one molecules to strike the adjacent molecules, that is lambda. So if number of molecules are less, in this particular case the number of molecules are less, so lambda is more, and if lambda is more, then definitely the Nansen number is greater than 0.01, and in this case the concept of continuum is not valid. So this is the one case where concept of continuum is not valid, right? Pressure is low, density low, so lambda is more. Now second case, in case of high vacuum. High vacuum means pressure is very lesser than the atmospheric pressure. High vacuum means pressure is less than the atmospheric pressure, right? Vacuum means pressure is less than the atmospheric pressure, and if I say high vacuum, so pressure at a particular point, pressure is very lesser than the atmospheric pressure, right? So in this case also the concept of continuum is not valid, right? So till this point it is clear to everyone, right? Whatever I discussed so far, that is clear to everyone. Tell me guys, whatever I had discussed so far, that is clear to everyone. It is crystal clear. It is crystal clear. Okay. Now come to the non-continuum. Come to the non-continuum fluid. Non-continuum fluid. This is out of the syllabus now. This is not a part of the syllabus. See, in case of the fluid mechanics, whatever the fluid mechanics will learn, okay, in our BTech level or for the competitive exam level, we assume the concept of continuum is valid, right? So in case of the non-continuum fluid, Kn is greater than or equal to 0.01. So again, this non-continuum fluid is categorized as 3 types of flow, right? This non-continuum fluid is again categorized as 3 types of flow. First one is the sleep flow. First one is a sleep flow. So if Nonsen number is greater than 0.01, right? If Nonsen number is greater than 0.01 but less than 0.1, then that non-continuum fluid flow is known as the sleep flow. That is a sleep flow. So for the sleep flow, Nonsen number value is in between 0.01 to 0.1, right? Second one is a transitional flow. So for the transitional flow, Nonsen number value is greater than 0.1 but less than 100. So in this case, the flow is, if Nonsen number value is in between 0.1 to 10, then such type of non-continuum fluid flow is known as the transitional flow. And third one is a free molecule flow. So in case of the free molecule flow, Nonsen number value is greater than or equal to 10. In case of the free molecule flow, the Nonsen number value is greater than or equal to 10, right? And if I want to show whatever we discussed so far, if I show that in form of the graph, right? So let us consider in this direction, in y direction, let us consider that is there is a fluid property. In y direction there is a fluid property. Let us consider that is a density. And in x direction, let us consider there is a lambda. What is a lambda? The lambda is a mean, or I can say L. That L is the characteristic length. So in x direction there is a characteristic length, and in y direction there is a fluid property, that is density. So beta, if see, let us consider this is the just 1 minute. Okay, this is 100 times of lambda. Here L is Here L is 100 times of lambda, right? Here that L is 100 times of lambda. So see, if L is less than 100 times of lambda, that means in this zone, beta, in this zone, the concept of continuum is not valid, right? Because L is less than the 100 times of lambda. So in this zone, concept of continuum is not valid. Concept of continuum is not valid. Is not valid. In this zone, concept of continuum is not valid. Now, if L is greater than 100 times of lambda, so in this zone, concept of continuum is valid. Concept of continuum is valid. Concept of continuum is valid. Right? Now see, in this zone where concept of continuum is not valid, it is not possible to define a unique density. It is not possible to define a unique density. Somewhere you are getting density, somewhere you are not getting density, somewhere you are getting density, somewhere you are not getting the density. So when the concept of continuum is not valid, it is not possible to define a unique density. It is not possible to define a particular density, right? Because at some point you are getting density, at some point you are not getting density, right? Where molecule is present, you are getting density. Where molecules is not present, you are not getting the density, right? But when the concept of continuum is valid, at every point you are getting the density. At every point you are getting the density. Is it clear? Right? This is the zone where concept of continuum is not valid. This is the zone where concept of continuum is valid. Right? So our focus in this zone. Our focus is in this zone, right? Where concept of continuum is valid, because we are dealing with the classical fluid mechanics. We are dealing with the classical fluid mechanics. We are dealing with the classical fluid mechanics. Right? In this zone, the statistical fluid mechanics come into picture. In this zone, statistical fluid mechanics come into picture. But in this zone, classical fluid mechanics come into picture. Is it clear to everyone? Okay. I hope beta everything is clear to you guys. This graph is clear to everyone now. This graph is clear to everyone now. Sorry. This graph is clear to everyone now. Tell me fast. This graph is clear to everyone now. Okay. Now come to the next topic, which is the fundamental properties of the fluid. Now let's start our discussion on fundamental properties of the fluid. So the first fundamental property is density or mass density. The first fundamental property of the fluid is density or mass density. So beta, what is the density actually? What density actually represent? Right? If I'm talking about the density, what is the density? Right? See, everyone knows the density. Density is the mass per unit volume. But what is the significance of the density? Can anyone tell me what density actually shows? So beta, density actually shows the measure of inertia. Right? Measure of inertia, or you can say measure of heaviness. Right? Measure of inertia or measure of heaviness. So let us consider, if I'm talking about the two substances, substance number A and substance number B. let us consider substance number A having density 700 kg per meter cube, and the substance number 2, substance number B having density, let us consider 7000 kg per meter cube. So from the value of the density we can comment that substance number 2 having more inertia, the substance number 2 is more heavy as compared to the substance number 1. Right, so actually the density or mass density, yes, from the we know that density is nothing but the mass per unit volume, we know that, but what is the actual significance of the density? The actual significance of the density, beta, it shows the inertia, or heaviness of a substance, and it is a ratio of mass per unit volume, and density is denoted by sorry, just 1 minute. Okay, density or mass density, na? Density or mass density. Density or mass density is denoted by rho. Density or mass density, it is denoted by rho, and it is simply mass. It is simply mass per unit volume. It is simply mass per unit volume. So mass per unit volume, right? And if I ask you what is the unit, what is the unit? What is the unit? What is the SI unit? What is the SI unit? That SI unit of the density is kg per meter cube, right? That SI unit for density is kg per meter cube. Okay, if I am talking about the MKS unit, so what is the MKS unit of the density? Kg per meter cube only, na? MKS unit is kg per meter cube only. If I am talking about the CGS unit, of density, so what is the CGS unit of density? So it is simply gram per centimeter cube. This is the CGS unit of the density. And what is the relation between CGS unit and the SI unit? Relation between CGS unit and SI unit. What is the relation between CGS unit and the SI unit? What is the relation? So the relation is, see, 1 gram per centimeter cube. So this is equal to 10 to the power minus 3 kilogram divided by, this is 10 to the power minus 6 meter cube. So ultimately we can write 1 gram per centimeter cube, right? 1 gram per centimeter cube is equal to 10 to the power 3 kg per meter cube, right? So this is the relation between CGS unit and the SI unit. Okay, now can we write the density in terms of the fundamental dimensions or primary dimensions? Yes, definitely we can write that density in terms of fundamental dimension. Fundamental dimension means in form of MLT. So this is nothing but the mass per unit volume, na? So ML minus 3. So this is the density in terms of fundamental dimension, ML minus 3. Now some example, right, or some value of density for some substances. So let us consider water. For water, what is the density? For water, the density is 1000 kg per meter cube. Right, for the water the density is 1000 kg per meter cube. And beta, this is the maximum density of the water. Right, this is the maximum density of the water. This is the maximum density of the water. The maximum density of the water occurs at 4 degrees Celsius. We know na? We know this. The maximum density, this is the maximum density na? Right. Whenever you write the density of water as 1000 kg per meter cube, so beta, this is the maximum density of the water. And the maximum density of the water occurs at the 4 degrees Celsius. Right. If you want to see the variation of density of water with respect to temperature, see here, density of water with respect to temperature, density of water with respect to temperature. So water has very, I can say there is a spatial pattern like this, right? This is the density variation of water with respect to temperature, right? So maximum density occurs at 4 degrees Celsius. Maximum density occurs at 4 degrees Celsius, and this value is 1000 kg per meter cube. 1000 kg per meter cube. Right. Now, if I am talking about the mercury, what is the density of mercury? What is the density of mercury? What is the density of mercury? Density of mercury is around 13600 kg per meter cube. So if you are comparing these two values, right, the density of the water and the density of the mercury, right, so you can comment mercury is heavier than the water, or mercury has more inertia as compared to the water, because density of the mercury is more as compared to the density of water. Right. Now if I am talking about the density of air, right, density of air, that is 1.05. This is 1.025 kg per meter cube at standard temperature pressure, at STP. Right. Now, so these are the some densities, these are the some values of density for some substances. Right. Now come to the effect of temperature and pressure on density. Effect of pressure. Effect of pressure on density. Effect of pressure on density. What happened if we increase the pressure? What happened if we increase the pressure? If we increase the pressure, then what happened with density? What happened with density? If we increase the pressure, then what happened with the density? Tell me guys, if you increase the pressure, that means in a given volume the number of molecules are more, no? Right. If you increase the pressure, let us consider a piston cylinder arrangement. Let us consider a piston cylinder arrangement. Right. Let us consider a piston cylinder arrangement. So let us consider there is a piston. Right. If the piston at this position number 1, let us consider pressure is P1. Let us consider pressure is P1. Now let us consider this volume. Let us consider this volume. When pressure is P1, the number of particles, number of fluid particles in this particular volume is, let us consider 5 volume. Right. Let us consider number of particles are 5 in this particular volume when the pressure is P1. When the pressure is P1, 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 the number of molecules in a given volume, let us consider 5 number of molecules. Now if we increase the pressure, so if we increase the pressure, so piston is moving to this particular point, right? Or we can say piston is at the state number 2, and at the state number 2 the pressure is P2. The pressure is P2, and P2 is greater than P1. P2 is greater than P1, right? When you are pushing the piston, then definitely pressure will increase. So P2 is greater than P1. Now tell me guys, when pressure is P2, then in this given volume, right, whatever the volume we consider, the number of molecules the number of molecules will increase na. Number of molecules will increase na. If you increase the pressure, then at this volume or in this volume the number of molecules will increase, and when the number of molecules will increase, mass is increased. So in a given volume, mass increases, so definitely the density increases. So when you increase the pressure, then yes, density increases. When you increase the pressure, density increases. Getting my point? So when pressure is P1, see, when pressure is P1, in a given volume, number of molecules, let us consider that is 5. When pressure you increase, let us consider the pressure is P2. In the same volume, the number of particles or number of fluid particles increases. So let us consider number of fluid particles is 10. Is it fine now? When pressure is P1, in a given volume, number of fluid particles 5. When pressure increases, in a given volume, in a same volume, number of particles will be 10. So number of particles increases, that means mass increases. So in a given volume, mass increases. So density increases. Density is mass per unit volume. Is it fine? Is it clear to everyone? Fine. So if I'm talking about the effect of pressure on density, of fluid, na? Of fluid. Effect of pressure on density of fluid. So when you increase the pressure, density increases. What happened with the temperature? Effect of temperature on density of fluid. Okay, I will do one thing. See the next slide. Effect of temperature. Effect of temperature on density of fluid. Right. So when temperature increases, what about the density? When temperature increases, what about the density? Now you can apply the same concept. Beta, you can apply the same concept, na? You can apply the same concept. See here. Again I am considering a piston cylinder arrangement. See, again I am considering a piston cylinder arrangement. Okay, so this is the cylinder, this is piston, right? This is the state number 1. At this state number 1, let us consider temperature of the fluid. temperature of the fluid particles is T1. Right? Now, again I am considering volume. So let us consider this volume. Let us consider this volume beta. Let us consider this volume. Let us consider this volume. Right? Now, when temperature is T1, in a given volume, number of molecules are, let us consider that is 3. Right? Now I am increasing the temperature. So for increasing the temperature, what I am doing here, I am providing the heat energy. Right? For increasing the temperature, I am providing the heat energy. Right? So temperature, when we are providing the heat energy, the temperature of the fluid increases, and when the temperature of the fluid increases, it will try to expand. Right? It will try to expand. Now, after expansion, let us consider this is the position of the, piston. Fine na? Okay. Now see, when you increase the temperature, so let us consider T2. So when you increase the temperature in a same volume V, right, T2 is greater than T1 na? Beta, T2 is greater than T1. So when you increase the temperature, in same given volume, the number of molecules decreases. So number of molecules decreases, that means mass decreases na? In a given volume, mass decreases, and in given volume mass decreases, that means density decreases. So when you increase the temperature, density decreases. Right? When you increase the temperature, density decreases. Is it clear to everyone? Beta, is it clear to everyone? Tell me. So effect of pressure on density. So when you increase the pressure, density increases, and when you increase the temperature, density decreases. Okay, now come to the now we are talking about the fluids, right? Whatever the discussion we made here, that is for the fluid. Now come to the liquids. Now if I am talking about the liquids, for liquids, so beta, either I am considering the liquid or I am considering the gases, right? Either I am talking about the liquid or I am talking about the gases. You increase the pressure, density increases. When you increase the temperature, density decreases. So for liquid also, when you increase the pressure, density increases. When you increase the pressure, density increases. So let us consider at a particular temperature. Let us consider let us consider 20 degrees Celsius. Right? Let us consider 20 degrees Celsius. Just 1 minute, na? Okay. Let us consider 20 degrees Celsius. Right? At 20 degrees Celsius, when pressure is 1 atmospheric pressure, I am taking example of water. Right? I am taking example of water. So whatever the value I am writing here, that is for the water. Right? So this is true. When you increase the pressure, density increases. That's fine. So corresponding to particular temperature, so let us consider that temperature is 20 degrees Celsius. So when the pressure is 1 atmospheric pressure, the density is 998 kg per meter cube. When the pressure is 1 atmospheric pressure, the density is 998 kg per meter cube. Now when I increase the pressure 100 times, that means 100 atm, then density of the water is 1002 kg per meter cube. 1002 kg per meter cube. Right? So here you can see corresponding to particular temperature, when you increase the pressure, density increases, right? When you increase the pressure, density increases. But what happened in case of the water? What happened in case of the water? When you increase the pressure 100 times, the density changes from 998 kg per meter cube to 1002 kg per meter cube. So pressure changes 100 times. But what about the density change? The density change is only 4 kg per meter cube. 4 kg per meter cube. So if you find the percentage change in density, if you find the percentage change in density, if you find the percentage change in density, so percentage change in density, that is 1002 minus 998 upon 998 into 100%. 100%. So tell me guys, what is the percentage change in density? Tell me, what is the percentage change in density? Tell me, what is percentage change in density? So tell me na in percentage. So tell me na in percentage. In percentage, 1002 minus 998 upon 998 into 100%. So it is 0.4%. It is 0.4%. It is 0.4%. 0.4%. So beta, can I say the change of density of water with change in pressure is negligible na? Right? Can we say change in density of water with respect to change in pressure is negligible na? You change the pressure, you increase the pressure 100 times. And corresponding to that, if you calculate the percentage change in density, the percentage change in density is 0.4%. Right? So beta, in case of the liquid, I am taking example of the water, but this is applicable for the other liquids also. Right? This is applicable for other liquids also. So I can say in case of liquid, beta, I can say in case of liquid, in case of liquids, change in density with change in pressure, change in density with change in pressure is negligible. Therefore, liquids are generally considered considered as incompressible. Therefore, liquids are generally considered as incompressible. Right? So if someone asks you why liquids are considered as a incompressible, so you can say in case of the liquids, change in density with respect to change in pressure is negligible. Therefore, liquids are generally considered as incompressible. Right? Therefore, liquids are generally considered as incompressible fluid. Is it clear, beta? Is it clear? Okay. Now, if I am changing the temperature corresponding to particular pressure, so let pressure is 1 atmospheric pressure. Right? Let pressure, right, for liquid only, na? For water only, sorry, for water only. When pressure is 1 atmospheric pressure, right, when pressure is 1 atmospheric pressure, and temperature is 21 when temperature is 20 degrees Celsius, and temperature is 20 degrees Celsius, temperature is 20 degrees Celsius. At this point, density is 998 kg per meter cube. When you increase the temperature, so let us consider temperature is 80 degrees Celsius. Corresponding to this temperature, density is 972 kg per meter cube. Right, there is no need to remember this value now. For you guys, there is no need to remember these values. For you guys, what is the important? For you guys, what is important? Right? Effect of pressure on density of the fluid. When you increase the pressure, density increase. When you increase the temperature, density decreases. In case of the liquid, change of density with respect to change in pressure is negligible. These knowledge is important, not these numerical values. These numerical values I am taking for example purpose only, for better understanding purpose only. Right? So these values are not important for you guys. Okay? So if corresponding to particular pressure, when temperature is 20 degrees Celsius, density is 998 kg per meter cube. When you increase the temperature, definitely density decreases. We know that when you increase the temperature, density decreases. So at 80 degrees Celsius, that water density is 972 kg per meter cube. So guys, if I ask you here, what is the percentage change in density? 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 Calculate the percentage change in density. So this is 998 minus 972 upon 998 into 100%. So this value comes around 2.60%. Yes, this value is around 2.6%. Right? So change of density with respect to change in temperature for liquid is significant. Right? In liquids, change in density with respect to change in pressure, with respect to change in temperature, is significant. So I hope you can understand this. Okay, now come to the gases. For gases, right? And we assume this gases as an ideal gas. Right? For gases. And we assume gas as an ideal gas. Right? Now see, in case of ideal gas, we can use the ideal gas equation, and that ideal gas equation is PV is equal to mRT. This is the ideal gas equation, PV is equal to mRT. Right? Or we can write P is equal to m by V RT, or we can write P is equal to rho RT, right? Where P is the absolute pressure, in kPa. V is the volume of container or volume of gas, in meter cube. Right? M is the mass of gas. Rho is the density of gas. or density of gas, and R is the characteristic gas constant. R is the characteristic gas constant, right? R is the characteristic gas constant. T is the absolute temperature, and that unit is kilojoule per kg Kelvin, right? T is the absolute temperature, and absolute temperature, that means in Kelvin scale, right? So P is equal to rho RT, right? Or we can say rho is equal to P, rho is equal to P RT, rho is equal to P RT, right? So at a given pressure, right, at a given pressure, if pressure is constant, if pressure is constant, pressure is constant, pressure is constant, that means isobaric condition. Isobaric, pressure is constant, that means isobaric. So when pressure is constant, then we can directly write density is directly proportional to 1 by T, right? So when you increase the temperature, density decreases, right? And if temperature is constant, that means isothermal condition. Temperature is constant, that means isothermal condition, right? Temperature is constant, that means isothermal condition. At this condition, rho is directly proportional to P. Rho is directly proportional to P. So beta, it is very much clear, right? It is very much clear. The gaseous density is very strong function of pressure and temperature, right? Gaseous density, we can say note point, gaseous density is a strong function of pressure and temperature. A strong function of pressure and temperature, right? Whereas in case of the liquid, right, density is not a strong function, or density is independent of the pressure. Density of liquid is independent of the pressure, but yes, it changes with temperature. But with respect to pressure, we can say that liquid density is negligibly dependent on the pressure, right? Negligibly dependent on the pressure, if I'm talking about the liquid density. Is it okay? Is it clear to everyone? So beta, whatever the discussion or whatever we discuss related to the density, that is clear to everyone. Whatever we discuss related to density, that is clear to everyone. Tell me fast. Okay, now come to the second property, right? Come to the second property, and the second property is weight density or specific weight. Weight density or specific weight. And weight density or specific weight, I am denoting this weight, specific weight or weight specific density or weight density or specific weight as gamma, right? Weight density or specific weight it is denoted by gamma. Right? It is denoted by gamma, and it is simply weight per unit volume, right? Mass density is mass per unit volume, and in a similar way, weight density is weight per unit volume, weight per unit volume. And weight, we can write weight as a mass into gravitational acceleration, right? We can write weight as a mass into gravitational acceleration, right? And volume, that is V. So weight density is equal to mg by V, right? Now this m by v, can I write this is equal to rho? This m by v, can I write is equal to rho? Can I write this is equal to rho? So gamma is equal to rho density multiplied by g. Gamma is equal to rho multiplied by g. So gamma is equal to rho multiplied by g, where rho is density and g is the gravitational acceleration. Okay, now come to the unit. So what is the SI unit for weight density? What is the SI unit? What is the SI unit for weight density? Can anyone tell me? What is the SI unit for weight density? So weight, right? Weight is Newton. Weight unit is Newton. And per unit volume, so Newton per meter cube, right? So SI unit for the weight density is Newton per meter cube. Now if I am talking about the MKS unit, so what is the MKS unit for the weight density? So in MKS system, we can write 1 Newton is equal to 1 kg meter per second square, right? In MKS system, we can write 1 Newton is equal to 1 kg meter per second square. So see, 1 Newton is equal to 1 kg meter per second square, right? And this is meter cube. So meter and meter is cancel out. So finally it comes kg per meter second square, right? Kg per meter second square. So this is the MKS unit. Now come to the CGS unit. CGS unit. Come to the CGS unit. So what is the CGS unit? The CGS unit is dyne per centimeter cube. Right? What is the CGS unit? The CGS unit is dyne per centimeter cube. This is the weight density unit. SI unit Newton per meter cube. MKS unit kg per meter square second square. And the CGS unit is dyne per centimeter cube. Can you write weight density in terms of fundamental dimensions? Yes, we can write. See here, this is nothing but the m L minus 2 T minus 2, right? This is the weight density in terms of fundamental dimensions, right? m L minus 2 T minus 2. Okay, can you establish the relation between CGS unit and the SI unit? Can you establish the relation between CGS unit, relation between CGS unit, and the SI unit? Can you establish the relation between CGS unit and the SI unit? Right? So 1 dyne per centimeter cube. See here, the CGS unit is 1 dyne per centimeter cube. 1 dyne per centimeter cube. This is equal to, and better we know that 1 Newton is equal to how much dyne? 1 Newton is equal to how much dyne? 1 Newton is equal to 10 to the power 5 dyne. 1 Newton is equal to 10 to the power 5 dyne. So 1 dyne is equal to 1 dyne is equal to 10 to the power minus 5 Newton. Right, so 1 dyne is equal to 10 to the power minus 5 Newton divided by centimeter, so centimeter cube, so 10 to the power minus 6 meter cube. So ultimately what you are getting, 10 to the power minus 5 plus 6 Newton per meter cube. So beta 1 dyne per centimeter cube is equal to 0.1, right? 10 to the power, sorry, minus 5 plus 6, this is 10 Newton per meter cube, 10 Newton per meter cube. So this is the relation between, CGS unit and the SI unit, right? 1 dyne per centimeter cube is equal to 10 Newton per meter cube. Is it okay? Now let us talking about the weight density of some substances. Example. So what is the weight density of water? If I am talking about the weight density of water, so what is the weight density of water? What is the weight density of water? Right, so we can write now weight density, so rho multiplied by G, and whenever G is not mentioned, whenever value of G is not mentioned, take value of G as 9.81 meter per second square. Right, whenever value of G is not mentioned, then take value of G as 9.81 meter per second square. So what is the value of gamma for the water? So this is simply 9.81 into 1000. So this is 9810 Newton per meter cube, or we can write 9.81 kilonewton per meter cube. Right, 9.81 kilonewton per meter cube. What is the weight density for mercury? What is the weight density for mercury? Weight density for mercury. So the mercury 13600 into 9.81. So 13.6 into 9.81. 13.6 into 9.81. 13.6 into 9.81. So this comes 133.416 kilonewton per meter. Kilonewton per meter cube. Right, now effect of temperature, effect of temperature and pressure, effect of temperature and pressure on weight density, effect of pressure and temperature on weight density of fluid is same as mass density, or simply density. Right, the effect of temperature and pressure is same as the mass density, because the only difference is G, and G is constant. Right, G is independent of pressure and temperature, and for the earth we assume G value is constant, and that is 9.81 meter per second square. So only difference between density and mass density is G. So if G is constant, then we can say the effect of temperature and pressure on weight density of the fluid is same as the mass density. Okay, now come to the next property, which is a specific volume. Come to the next property, that is a specific volume. So what is the specific volume? What is the specific volume? So specific volume is nothing but the total volume per unit mass, and specific volume is noted by small v. Specific volume is denoted by small v. The total volume is noted by capital V, and the specific volume is noted by small v. So we can say that specific volume is equal to, this is total volume per unit mass, right? So V is equal to, this is V by M, right? Can we write in this way also? This is 1 upon M by V. Can we write in this way also, that specific volume is equal to 1 upon M by V? And we know that M by V, right? We know that M by V is nothing but the density. So we can say the specific volume is equal to 1 by rho. So from here we can define the specific volume in this way also, that specific volume is nothing but the reciprocal of the density, right? Specific volume is nothing but the, we can define in this way also. Now it is defined as the total volume per unit mass, or specific volume is reciprocal of density or mass density, right? Specific volume is reciprocal of density or mass density. Fine. Now what is the unit? What is the SI unit? What is the SI unit? So that SI unit is simple now. SI unit is meter cube per kg, right? Meter cube per kg. What is the MKS unit? MKS unit for specific volume. This is also meter cube per kg. What is the SI unit? What is the CGS unit? So CGS unit is centimeter cube per kg, right? And we established the relation between SI unit and the SI and CGS unit, right? Relation between SI unit and the CGS unit. So what is the relation? So we can write the centimeter cube per kg. I'm sorry beta. Centimeter cube per gram. Centimeter cube per gram. Right? Centimeter cube per gram. Right? 1 centimeter cube per gram. 1 centimeter cube per gram is equal to, this is 10 to the power minus 6, right? 10 to the power minus 6 meter cube divided by, this is 10 to the power minus 3 kg. So ultimately we can write 1 centimeter cube per gram is equal to, this is 10 to the power minus 6 plus 3. So this is minus 3 meter cube per kg. So this is the relation between SI unit and the CGS unit, right? Can we write in terms of fundamental dimension? Can we write a specific volume in terms of fundamental dimensions? Fundamental dimension. Fundamental dimensions. Can we write a specific volume Specific volume in terms of fundamental dimensions, yes, we can write. So specific volume is equal to, or specific volume, so this is m, this is L cube m minus 1, right? L cube m minus 1, L cube m minus 1, right? Right. Now can we compare can we compare the specific volume of liquid and gases? Can we can we compare the specific volume of liquid and gases? सर गेट एक्सी 50 मार्क्स पर आईआईटी बॉम्बे मिल सकता है क्या? मिल सकता है, मिल सकता है. Can we compare the specific volume of liquid and gases? Beta, if I ask you relation between specific volume of liquid and specific volume of gases, liquids and gases, can we compare? Can we compare the specific volume of liquid and specific volume of gases? Can we compare? Right, see here. In general, if I ask you what is the relation between liquid density and the gas density, what is the relation between liquid density and the gas density? Which one is more? Which one is more? Liquid density is more as compared to the gas density, or gas density is more as compared to the liquid density, or liquid density and the gas density are almost equal to same? No, right? We know that liquid density is more as compared to the gas density, na yaar? Liquid density is more as compared to the gas density, right? See, if you take example of water and the air, we know that water density is 1000 kg per meter cube. We know that density of water is 1000 kg per meter cube, right? And if I'm talking about the air, air density is around 1 kg per meter cube, around 1 kg per meter cube. That means water is 1000 times more denser as compared to the air, right? So obviously the density of liquid is more as compared to the density of gases, right? So if we know the relation between the densities of liquid and gases, so we can comment on the specific volume of liquid and gases. We can comment, right? So since the density of the liquid, since density of the liquid is very greater as compared to the gases density, right? And specific volume is the reciprocal of the density, right? So we can say that specific volume of gases is more as compared to liquids. Specific volume of gases is more compared to gases. Why? Because density of liquid is greater as compared to density of gas. Right, now in some time, right, I will tell you the very famous question of interview, right? That interviewer asks one very famous question. Let us consider two pipes in a room. Let us consider two pipes in a room, right? This is the pipe number 1. This is the pipe number 1. This is the pipe number 1. Pipe number 1. And this pipe number 1 has diameter small d. This is the pipe number 2, and pipe number 2 diameter is capital D. Right? This is very famous interview question. pipe number 1 has a diameter small d, pipe number 2 has a diameter capital D. This is a pipe 2, right? And capital D is greater than small d. Capital D is greater than small d. Now in one pipe, right, in one pipe liquid is flowing and in another pipe gas is flowing. Can you tell me in which pipe liquid is flowing and in which pipe gas is flowing? Right? Out of these two pipes, it is clear in one pipe liquid is flowing and in another pipe gas is flowing. So can you tell me in which pipe liquid is flowing and in which pipe gas is flowing? Can you answer this question? Beta, can you answer this question? So tell me first, question is clear or not? Tell me, question is clear or not? Tell me, question is clear or not? In which pipe liquid is flowing and in which pipe gas is flowing? So beta, this is very simple logic. See here, since, right, I'm giving the answer, since specific volume of gases is more, as compared to, since specific volume of gases is more as compared to specific volume of liquids, therefore to carry or to handle the gases, large diameter pipe is required. Large diameter pipe is required. Right? Since specific volume of gases is more as compared to specific volume of liquids, therefore to carry or handle the gases, large diameter pipe is required. So in pipe number 2, the diameter is more. That's why we can say in pipe number 2 gas is flowing. In pipe 2 gas is flowing, whereas in pipe 1 liquid is flowing, right? Is it clear to everyone? Is it clear? Exactly. Practical example, or even in air conditioning unit also, right? In air conditioning unit also, there are two pipelines. One pipeline is for the liquid refrigerant and another pipeline is for the vapor refrigerant, right? In AC, in air conditioning unit also, right? If you see in the indoor unit, right, there are two pipelines. One pipeline is for the liquid refrigerant and another pipeline is for the vapor refrigerant, right? And one pipe having lower diameter and the another pipe having larger diameter, right? So from the experience or from the knowledge, we can say that a small diameter pipe is for the small diameter pipe is for the liquid refrigerant and for the capital diameter pipe is for the vapor refrigerant. Okay, fine. So what topics we discussed today? First we discuss about concept of continuum. First we discussed about concept of continuum. Today first we discuss about the concept of continuum. Then we discuss about the fundamental properties. We discuss about the density. We discuss about the weight density. We discuss about the weight density. We discuss about the specific volume. So in tomorrow's class, we will discuss another fundamental properties like, right, in tomorrow's class, we will discuss another fundamental properties like specific gravity, relative density, and then viscosity, right? And in the viscosity in the viscosity topic, we will discuss about the Newton's law of viscosity and the number of examples related to Newton's law of viscosity. So beta, whatever we discuss in today's class, that is clear to everyone. Whatever we discuss in today's class, that is clear to everyone. That is crystal clear. Okay. Okay, so thank you so much for this session. So we will meet tomorrow at the same time and same channel. So thank you so much everyone, and bye bye, take care, and good night everyone. Good night.